Hi everyone, welcome back. In this video we're going to talk about surface integrals of vector fields. So before we do that, let's just revisit the line integral of a vector field. And so when we did line integrals of vector fields, the way we compute them was as an integral from a to b, where our parameter t was taking values, our parameterization for the curve plugged into our vector field, dotted with the derivative of our parameterization. Okay, so different than what we did for scalar line integrals. And here the orientation of the curve mattered. So you can traverse a curve two different ways. If you change direction, that changed the sign of your answer. Something similar is going to occur with surface integrals. So for surface integrals, the analog of having a curve being traversed one way or another is we need to be able to choose an orientation of our surface. So we need our surface to be orientable. And what that means is that we need our surface to have two distinguishable sides. And so you might ask yourself, well, is it possible for a surface not to have two distinguishable sides? Isn't that what it means to have a surface? And it is possible. So I have here a Mobius strip, kind of the easiest example of something that's non-orientable. And this Mobius strip only has one side. If I were to start traveling along this Mobius strip, I just draw a line here. Traveling, still traveling. Eventually, I end up back where I started. So this Mobius strip only has one side. It's not orientable. So we need our surfaces, when we do surface integrals, to be orientable. So we can't have weird things like Mobius strips or other weird surfaces that can occur. If you have an orientable surface, there are two choices of orientation, and this depends on the normal vector. So you can, if you have a surface with two sides, you can either pick the normal vector on one side of the surface or the normal vector on the other side of the surface. So for these surface integrals of vector fields, the direction of the normal vector matters. And we're going to need to be aware of which normal vector to pick. Now, if we have a parameterization for our surface, some function ruv, where u and v are our parameters, then the two unit normal vectors are given by the partial derivative of r with respect to u crossed with the partial derivative of r with respect to v divided by the magnitude of that cross product, or the partial derivative of r with respect to v crossed with the partial derivative of r with respect to u divided by the magnitude of that cross product. So these are unit vectors, and they're going in opposite directions. Remember that if you switch the order of a cross product, all you're really doing is multiplying by -1. So these are two normal vectors pointing opposite directions. So we're going to need to know which one of those to pick. Now, the question is, how do we know which normal to pick? Well, the problem should tell you which orientation to use. You shouldn't just be left to guess. There should be some indication, or the context of the problem should tell you which orientation you want. And after you know which orientation you want, there are two ways to pick. So you can use the right-hand rule, which we learned at the beginning of the semester. Remember, the right-hand rule was put the edge of your right hand on the first vector, so your fingers curl around towards the second vector, and your thumb points the direction of the cross product. And in this case, the thumb is going to be the normal vector. The other way is to guess and check. There are only two possibilities. So you compute one of them, and then check and see if that's the correct normal by plugging in a point. If it's the wrong normal, then you just multiply by -1, and you have the right one. So we have two possible orientations for a surface, and these two orientations have names, a positive or a negative orientation. Just like for curves, closed curves, we had positive or negative orientations. We have the same thing for surfaces. So a positive orientation means our normal is pointing upward, or it's pointing outward from the surface. And a negative orientation means the normal is pointing downward or inward. And it depends on what kind of surface you have. So here we just have some kind of shell, and this normal is pointing upward. That's a positive orientation. If this normal was pointing downward, so kind of inside this shell, that would be a negative orientation. Here we have a cylinder. So if I draw a normal, upward doesn't really have a meaning because all of these normals are going to be horizontal. But it's a negative orientation because it's pointing inside the cylinder. If I wanted a positive orientation, I would pick a normal pointing outside the cylinder. So those are the differences between the two orientations. Now, when we talk about surface integrals of vector fields, the kind of surface integrals we're going to be computing are flux integrals. We saw flux integrals before for curves. We talked about the flux across a closed curve. Now we're going to talk about the flux across a surface. So how a vector field is pushing particles across a surface. And this surface integral, the only surface integrals we're going to compute are going to be flux integrals. So f dot n d sigma. So given a parameterization for this surface S, we can plug that parameterization into F, we can compute that unit normal, and we can compute d sigma the same as we did for scalar surface integrals. But actually we can do better, because if we have a parameterization, and let's just say I know this is the unit normal that I want, I know d sigma is the magnitude of these cross products of partial derivatives that we've talked about before. I plug all of this in. I'm integrating over d, which is my parameter space. I plug the parameterization into my vector field. Here's my normal. It's the cross product divided by its magnitude. But then I'm multiplying by the magnitude, because that's part of d sigma. So these magnitudes are going to cancel out. So when we do surface integrals of vector fields, you don't ever have to compute this magnitude. All you have to do is compute the cross product, dot it with the parameterization plugged into your vector field, and you just compute this dot product. But now the order that you set up this cross product matters. Before it didn't matter because we were taking a magnitude. Now it does matter, because if I switch this order, a -1 is going to pop out. So you need to make sure you're picking the correct normal, set up this cross product in the correct way. And this is how we're going to compute these flux integrals across surfaces. Alright, let's take a look at an example. Find the flux of the vector field xyz over the sphere of radius 3 oriented outward. So our first step is to parameterize the surface. Since we have a sphere, let's use spherical coordinates. So I need to figure out how to reduce the variables by 1. But if it's a sphere, then rho is fixed at 3. So if I plug in spherical coordinates into my parameterization, I'm going to have 3 sine u cosine v, 3 sine u sine v, 3 cosine u. That parameterizes the sphere. Here I'm using u as my phi variable, so u only goes from 0 to pi, and I'm using v as my theta variable, so v goes from 0 to 2 pi. Okay, parameterize the surface. Our next step is to calculate the correct normal vector. And I'm going to go through both methods here, using the right-hand rule and then guess and check. So to use the right-hand rule, you need to conceptually know how the parameters are traveling along this object. So your first step is going to be to draw your surface, which I've done here. Let's pretend that's a sphere of radius 3, and determine the directions in which the parameters increase. So this might be a little challenging, but if we look at a sphere, our u variable is the same as a phi in spherical coordinates. So I know that phi is 0 in the positive z-axis, and then as we travel in this direction and get to the negative z-axis, it increases to pi. And that does that no matter which direction I go down the sphere. So u, my phi variable, is increasing in this direction. And that's why I've drawn these red arrows to indicate that this is the direction that u increases. V is my theta variable, and we know theta increases counterclockwise in the xy plane. So v is going to increase counterclockwise in the xy plane. So that's why I've drawn these black arrows to indicate the direction that v is increasing. Now I need to know the direction that my parameters are increasing, because this is the direction that the partial derivatives of r are going to go. When I take partial derivatives of r, it gives me a vector going in the direction that the parameter increases. So the next step is to pick a point and draw these partial derivatives. So I picked this point here, and I drew the partial derivative of r with respect to u going this way, because u is going to increase along the sphere down this direction. So the partial derivative goes downward in this direction. And then I drew the partial derivative with respect to v going this direction, because here v is going around this portion of the sphere counterclockwise. So this is the direction the partial derivative with respect to v goes. And now it looks like they're orthogonal, but they're not. They'll give you a normal. That's just the way I drew it. I'm going to use the right-hand rule to figure out which normal I want. So using the right-hand rule, I'm going to put the edge of my right hand on one of the vectors so that my fingers go towards the other one through the smaller angle between them. So if I choose RU, I would put my hand on the edge of RU, curl around to RV, and my thumb is pointing up. That's the normal vector we want. That's outward. If I were to put my hand, the edge of my hand on RV, I'd have to put it this way, curl around to RU, and my thumb is pointing down into the sphere. That's not what we want. So the correct normal is the partial derivative of r with respect to u crossed with the partial derivative of r with respect to v. Now, if I want to use guess and check, I'm just going to start computing things. I already know which is the correct normal vector to compute, so I'm going to compute that one anyway. But let's just pretend I hadn't done any of this, and I just start computing this normal vector. So I take some partial derivatives. I get the partial derivative with respect to u, the partial derivative with respect to v, and you can verify these yourself because there's the parameterization. I set up my cross product. It involves lots of trig functions, so we need to be careful. So I'm going to work this all the way out. The first component, I get 0 minus negative 9 sine squared u cosine v. So that's minus a negative becomes plus. Then I put a negative here. For the second component, I get 0 minus negative 3 sine u times negative 3 sine u sine v. That becomes minus positive 9 sine squared u sine v. And then for the third component, I get 3 cosine u cosine v times 3 sine u cosine v. So that's 9 sine u cosine squared v minus 3 cosine u sine v times negative 3 sine u sine v. So minus a negative becomes plus 9 sine u sine squared v. And here you notice I have a 9 in all three components, so I can factor that out because these zeros are going to disappear. I can factor a sine u cosine u out of these two terms, and I'm left with cosine squared plus sine squared, which is just 1. So this simplifies to 9 times the vector sine squared u cosine v, sine squared u sine v, sine u cosine u. So now I've computed one of the normals. I want to check and make sure I have the right normal. So I need to pick a value for u and v where I know what the normal should be. So for example, let's just say I want to pick the normal pointing in the positive x direction. So I want to pick the point where the x-axis intersects this sphere, the positive x-axis. And I know the normal should be pointing outward, so it should be pointing the same direction as the x-axis, meaning the first component should be positive, the next two components should be 0. So I need to figure out the values of u and v that give me this point. So I get the normal pointing out in this direction. Well, for v, v is the same as theta. V is going to be 0 because I know v gives me an angle with the positive x-axis. So here v is 0. U is an angle with the positive z-axis. Well, this is a 90-degree angle, so my u value is going to be pi over 2. And now I can check plugging in pi over 2 for u and 0 for v. So sine squared of pi over 2 is 1. Cosine of 0 is 1. So this first component is just 9 because I have to multiply this 9 through. Sine squared of pi over 2 is 1. Sine of 0 is 0, so this is 0. Sine of pi over 2 is 1. Cosine of pi over 2 is 0, so this is 0. So when I plug in that point, I get the vector 9, 0, 0. It's pointing outward, out of the sphere, so that is the correct normal, and that's how you could use guess and check. Okay, and that's probably the most difficult part of computing these kinds of surface integrals. What's left is plugging the parameterization into our vector field. In this case, this is super simple because our vector field was just x, y, z. So when we plug our parameterization in, we just get the parameterization back because I always plug in the first component for x, the second component for y, the third component for z. So this is exactly r. So that's our vector field on the sphere. And now I need to set up my integral and integrate. What I'm going to do here is I'm going to factor a 3 out of this vector field, so that 3 is there, and there's my parameterization plugged into the vector field, which in this case is the same as the parameterization, dotted with the normal vector, or the cross product that we computed, and I have a 9 sitting out there. I'm integrating with respect to u and v. U goes from 0 to pi, v goes from 0 to 2 pi. Now I need to compute that dot product. I'm going to pull the constants out, so 3 times 9 gives me 27. If I compute that dot product, I'm going to get exactly sine cubed u cosine squared v plus sine cubed u sine squared v plus sine u cosine squared u. Now I'm going to start factoring things to simplify this. You could go ahead and integrate as is, but it's going to be pretty complicated. So instead, let's see if I can get some simplifications by factoring. I'm going to factor a sine u out of all three terms, and then I'm going to focus on these two terms and factor out a sine squared. So it's going to look like this. Here's the sine u I factored out of all three terms. Then the first two terms I just factor out a sine squared u. So what's left is a sine squared v plus cosine squared v of the first two terms. That just gives me 1. And then what's left after I plug in a 1 here, I have sine squared u plus cosine squared u. Because when I factored out this sine u from the third term, all I'm left with is cosine squared u. But sine squared u plus cosine squared u is also 1. So really all I'm integrating here is sine. So I integrate that in u, I get negative cosine. I evaluate from 0 to pi. When I plug in the bounds, that gives me 2. I can factor this 2 out, and that's going to be 54 times the integral of 1 over the interval 0 to 2 pi, which is just 2 pi. So my answer is 108 pi. All right, so there's an example of a flux integral. In the next video, we'll finish up this section by looking at more flux integrals.